There was nothing, no stars, no light, nothing. For 200 million years after the Big Bang, the universe sat in total darkness. Not nighttime dark, not the darkness between stars, a darkness with no stars at all, anywhere. The entire observable universe, blind. 200 million years. No photon, no glow, no warmth, just hydrogen and helium, drifting, cooling, waiting. And then, something ignited, the first star, a monster 100 times more massive than our sun, 17 times hotter, burning so violently it would be dead within 2 million years. Nobody saw it, nobody named it. And when it died, it didn't leave a corpse. It detonated and scattered the first carbon, the first oxygen, the first iron, into a universe that had never contained them. For 60 years, these stars were purely theoretical. 2 weeks ago, we may have finally found them. And the story of how we got there changes everything you think you know about where you came from. To understand what was found, you need to understand what came before. And what came before was silence. 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. Protons captured electrons. Hydrogen appeared. And in that moment, the universe released a flash of light. The cosmic microwave background. The oldest light that exists. After that flash, nothing. The universe went dark. Cosmologists call this period the Cosmic Dark Ages, and it lasted longer than most people realize. For roughly 200 million years, 20 times longer than the age of the dinosaurs, there was no light source anywhere in the observable universe. Just clouds of hydrogen and helium, slowly clumping together under gravity, drifting in absolute cold, absolute dark, absolute quiet. And then, in the densest pockets of gas, something began to happen. Dark matter halos, invisible structures of gravitational scaffolding, had been forming since the beginning. And inside the densest of these halos, primordial gas began to fall inward, heating, compressing, reaching temperatures and pressures that had never existed since the Big Bang itself. But here's what made these first collapses different from anything that happens today. The gas was pure, perfectly, absolutely pure. 75% hydrogen, 25% helium, trace amounts of lithium, 0 carbon, 0 oxygen, 0 iron. These elements didn't exist yet, because they can only be made inside stars, and no star had ever existed. That purity changed everything, because without heavy elements, gas can't cool efficiently. It can't fragment into small, well-behaved stars like our sun. Instead, it collapses into something else entirely, something monstrous. Astronomers call them population 3 stars, not because they came third. The naming is backwards, a historical accident. Population I are stars like our sun. Population 2 are older, metal-poor stars in the galactic halo. Population 3 are the originals, Generation 0, the ancestors of everything. And they were enormous. Where our sun sits at 1 solar mass, population 3 stars range from 10 to possibly 1,000 times more massive. The models that best match what JWST just found suggest a sweet spot between 10 and 100 solar masses. Each one a thermonuclear furnace of a scale the modern universe simply doesn't produce anymore. Their surface temperatures reached 100,000 Kelvin, our sun's surface 5,800. These stars were 17 times hotter. So hot they emitted radiation energetic enough to rip electrons off helium atoms twice, a process that requires photons above 54 electron volts. For context, visible light carries about 2. They burn through their fuel in under 2 million years. Our sun will last 10 billion. These stars lived fast, burned everything, and then did something the universe had never seen. If you're still with us, good. Because this is where the story stops being about astronomy and starts being about you. When a population 3 star between 140 and 260 solar masses runs out of fuel, something unique happens. At the core, temperatures become so extreme that gamma rays begin converting into pairs of electrons and positrons, matter and antimatter, appearing out of pure energy. This drains the radiation pressure holding the star up. The core contracts, temperatures spike, and then runaway thermonuclear fusion ignites the entire star. Not a supernova that leaves a neutron star behind, not a collapse that forms a black hole. The entire star, every atom is blown apart. Cosmologists call it a pair instability supernova. It is the only type of explosion in the universe that leaves zero remnant. The star doesn't just die, it erases itself. And in that detonation, it scatters something the universe has never contained: carbon, oxygen, silicon, iron, the first heavy elements. Flung into the surrounding gas at thousands of kilometers per second, those atoms mix with the primordial hydrogen. They cool the gas, they allow it to fragment. And from those fragments, a new generation of stars is born. Smaller, longer-lived, capable of forming planets. And on at least one of those planets, capable of producing life. Every carbon atom in your DNA, every oxygen molecule you're breathing right now, every iron atom in your blood, all of it was forged in the death of a star that no one ever saw. A star that existed for less than 2 million years, 13 billion years ago. For 60 years, population 3 stars were a prediction. Every model of the early universe required them to exist. Without them, there was no way to explain where the first heavy elements came from, no way to explain how the cosmic dark ages ended, no way to explain how galaxies formed. But no one had ever seen one. Not even a trace. Then, the James Webb Space Telescope pointed its infrared spectrograph at a galaxy called GNZ11, one of the most distant galaxies ever observed, 13.4 billion light-years away. The light arriving at the telescope had been traveling since 430 million years after the Big Bang. JWST stared at this galaxy for 38.8 hours, almost 2 full days of exposure time, focused on one tiny patch of sky. And in the data, Roberto Maiolino's team at Cambridge found something extraordinary. Near GNZ11, they detected a small companion object. They named it Hebe, after the Greek goddess of youth, the youngest thing we've ever found. Hebe was glowing in doubly ionized helium, a signature that requires temperatures only population 3 stars can produce. The detection, 6 sigma. In physics, 5 sigma is the threshold for discovery. This was above it. A second team, Rusta and colleagues in Florence, independently confirmed the signal with a different spectral line. Hydrogen gamma, 5.9 sigma. Same location, same object. 2 teams, 2 methods, 1 answer. And here's what sealed it. In the entire spectrum of Hebe, there was not a single metal line, no carbon, no oxygen, no nitrogen, no iron, nothing. Every known object in the universe, every star, every black hole, every nebula, produces metal emission lines. Hebe produced none. The composition was pure, primordial, unchanged since the Big Bang. Exactly what population 3 stars would look like if they existed. But, and this matters, the papers haven't passed peer review yet. The word the teams use is the strongest evidence yet, not proof, not confirmation, the strongest evidence. And after 60 years of searching, that distinction matters. Because here's the thing about the first stars. Even if Hebe isn't the final answer, the question it asks is one of the most profound in all of science. Before there was a sun, before there was an Earth, before there was a single molecule of water or a strand of DNA, there were stars, burning alone in a universe that had been dark for 200 million years. They had no audience, no planets, no life to witness them. They burned, they died, they scattered their atoms into the void, and from those atoms, eventually, billions of years later, came everything, including you. You're now one of the few people who knows what ended the longest darkness in the history of the universe. Most people will live their entire lives without ever hearing this story. If that changes the way you look at the night sky tonight, stay, subscribe. Next week, we investigate an object that entered our solar system from another star, and 8 years later, Harvard's top astronomer still thinks it might have been built by someone.